get started. So we're trying to finish the algorithm that we sort of introduced last time without any justification, which was expectation maximization, and we're trying to get to principal component analysis of this. So in all, I think, practical purposes, this will be the last class where we're introducing any sort of new material to you. On Wednesday, I think if we have something left, I think a little bit of PCA will be left. We'll just finish that and talk about advanced topics that are relevant for, we'll give you a hint of what comes next in sort of other machine learning classes. It won't be part of the training of all this stuff, so we won't test you on most of that stuff. Okay. So just a reminder, your poster presentation is Friday. The room's confirmed. We have all the logistics figured out. I never thought I'd be so excited about poster boards, but yes, we have those figured out. You already have my email about poster sizes. Please get started quickly. Get in touch with Brandon. The instructions for printing, if you're in EC, the instructions for printing, poster printing are available online from the computing and EC. Okay. All right.
The dimensions are changed, right?
Yeah, the dimensions are. Thank you. I'll just fix that. So you have a final, what is that? You have a final exam. It's scheduled right now, according to the registrar, on May 11th, which is Monday morning, from 7:30 a.m. to 9:30 a.m. I would rather not torture people who may be a little bit more nocturnal. Or at least more normal. So I've arranged for a different room, but I know the way registrar schedules this, they are guaranteed of a conflict-free arrangement. As soon as I try to change something, I have to ask him. So does that time work? May 12th, 2 to 4 p.m.
Yeah.
Yes.
Yeah.
No? Okay, so that's the new time. It's at Kelly Hall 310. Yes. You have a conflict?
Yeah.
You have a conflict?
Might.
You might have a
Because we have AI exam and that is like online, you take it, then you have to submit it by after 48 hours. And the last date, like last time is end of the day 13th. So if we have ML there, we won't have 48 hours and we can't take it before this. So a bunch of other things scheduled.
Let's do it after 14.
not possible. 15th is when we need to upload the grades and stuff. I can't give Ching a day to grade everything.
Can I take it?
We could do May 11th. I'll have to get. I really don't want it to be that. Like if you really wanted to take it 7:30, Ching will have me show up. But I would rather do one session instead of 2 exams. So when does AI start?
You can start any time, but the last time when you can submit is end of the day 13.
So I don't hear a conflict yet.
If we take it, we won't have 48 hours, right? If we take the exam on 12, because
when is it released?
anytime you just send an email and you will get the exam.
Oh, I see. So you could ask for the exam to be released this Friday, for example, as soon as you get done with the poster session.
Yeah, but there are other things.
But we have everything.
Yeah.
Okay, so let me try to do this. Now I'll try with 13. Sorry, let me get back. What was your conflict?
You have to give a test.
You have to give a thesis.
No, I have students and I'm proctoring my test.
Oh, I see. Okay. All right, this is going to be tricky. What about the 13th? Is 13th open for?
No. Got a flight. Got a flight.
Sorry, are there any conflicts for 13? Yes?
Got a flight.
Maybe you're leaving.
Yeah.
You're leaving. Okay. So the registrar time will have to hold. I tried.
So May 11 some other time is not possible. Maybe
maybe I can have somebody else proctor for me.
But your conflict is on the 12th, not 11th.
May 11 some other time.
Here's what I'm going to do. I'm going to find another time on May 11th, and I'm going to have a different, like maybe that time on May 12th, and I'll send out a poll, and then we'll see whether there are any comments, right? Okay. If I have to make sure that everybody gets a chance, and so unfortunately this is one of those things that if people have a conflict, then I'd like to schedule one thing, and so I don't want to force people to do some. So our recourse will be the registrar appointed time, which is okay. All right, we'll do this over email then. All right. Okay. Sorry, just to get back, it's going to be a similar thing as the midterm. It's going to be open book, open notes, pen and paper. You won't need calculators. You can bring them if you like. It's closed internet. We'd like you to not bring any electronic devices. Your phones are fine. Your laptops, if you really need to access the PDF on the thing, is okay, but please don't connect to a browser or anything. The material is going to be everything with a focus on the recent stuff. I want to say maybe it's exponentially decaying with some bandwidth parameter. That's up to me to decide. Here's what I'd like to convey. It's not going to be as hard as the midterm. So. Yeah.
You mean the lengthwise?
So the length may actually be nearly identical to the midterm, except you have 2 hours to do this, right? But I don't know. But my philosophy is that the parting interaction of a semester should not be.
Will we get our midterms back before then? So we can see what we did?
Yeah. Your midterms have been graded. Sorry, I guess I just never sent out an email that you can pick them up. Yes.
Oh, okay.
Yeah, you can pick them up.
Okay.
Yeah, they have been graded. That's why we have to. Yes. Send an email.
Homework 3 solutions?
Have the homework solutions not been released? Yes. So the homework solutions of the grades will be done by tonight. Yes, I talked to Cheng about that. We should have that out soon, and we'll try to have the homework for solutions out this week, so you can look at the solutions. The actual grading may not be done by the time you find it, but you'll have the solutions so that you can study. Any other questions about it? Yes.
If we have extra days that we can use for the poster.
Not for the poster, not for the exam. I think we spelled those out pretty clearly. I've been here.
Can you borrow extra days from someone else?
No, you cannot. I'll have to remember this one. For next year, I'll explicitly state no borrowing.
There's still a black market.
Yeah, I want to make it perfect. Okay, maybe I should.
You can feel free to, we allow infinite resubmissions. Feel free. Okay. I want to move on from this. Just one quick thing. I mean, it's not going to be a trivial final, but it's not going to be really hard. I expect this to be, focus on the newer stuff. Look at the midterm. That's the kind of questions that you should expect. It will not be too long. We don't anticipate you taking all 2 hours to do it. It may, some parts of it may be difficult. That's fine, but we don't expect the entire exam to be really difficult. That's not the point. I think we've covered the entire semester. Whatever you've learned. At this point, we're beyond the point of sort of shock and all, right?
One.
Yes.
Will there be like extra credits as?
There'll be some, not as much as some of the homeworks, but yeah, there'll be some extra. Okay. All right. So let's dig in. So what we are trying to do last time we looked at clustering. We looked at a particular algorithm that was called K-means. There's this iterative sort of easy algorithm where you were given some data set, you were told some K, and you were asked to assign every data point to a cluster center, but you don't quite know what a cluster center is, and you have to sort of figure out what a cluster center is and solve the assignment problem. And we sort of did that in an alternating manner, right? If someone told me where the cluster centers were, I can easily do the assignment. That's the min distance problem. If someone tells me all the assignments to a cluster, I just have to re-estimate the center. That's just a averaging problem. find the average. We interpreted that as coordinate descent on a particular objective. We said, here's the objective, it's sort of this distance objective, distance from a data point to the assigned cluster center, and if you want to minimize both the assignment variables and the cluster center variables, you alternate between the two, and it's coordinate. And we've sort of then made this transition from here to Gaussian mixture models. On surface, the problem changed from clustering to density estimation, because clustering had no notion of probabilities. It was just sort of this types of input problem. And this was a fitting a probability density function. But as soon as we dug in a little deeper, we realized that the algorithm, which we sort of just gave an overview, the algorithm for fitting Gaussian mixture model parameters looked exactly like k-means, or it looked like a soft version of k-means, right? It also had two steps. Instead of an assignment and a centering step, it was a E step and an M step, expectation and maximization, and we'll tell you today why they're called expectation and maximization. One was estimating the probability that a data point is assigned to a cluster given the X and the current parameters. So this should have comma current parameters, and then maximizing full likelihood. So this maximizing full likelihood we've already done in previous classes. We know that when you tell me what data points are assigned to a Gaussian, I just have to compute means, right, and covariance matrices. And we visually looked at an example of that. This is what that looks like. You initialize 3 Gaussians, so these are covariance matrices plotted here with iso curves. And what we said was the algorithm alternates. So these are the initializations. These are 3 prior variables for each of the Gaussians. And we said for each data point, this pie chart shows probability of z given x. How much does this data point, how likely is this data point to belong to one of these Gaussians? To belong, or what, in the sort of algorithmic sense, but in the probabilistic sense, what is the probability that that z for this variable is, this latent variable is set to that Gaussian? Right? So something here, because it's right underneath the mass of all 3 of those Gaussians, it's nearly uniform. Something here is only assigned mass by this particular Gaussian. So it's nearly p. Right? Given this assignment, you get to re-estimate the parameters of all 3 Gaussians. So the green stuff seems to be centered here, so we expect the green Gaussian to move. The blue stuff seems to be centered here, and there's just a little bit of extra mass on the red stuff that is here, so we expect the red to shift there. Okay. And that's what happens. As you sort of keep re-estimating the conditional probabilities of z given x and of the parameters of the Gaussian, you sort of end up with this sort of a convergence. That makes sense? Okay. So this is where we were last time. We already gave you the algorithm. We called it EM. Today we'll justify why we're doing this. Okay. But before we do that, I want to quickly mention that this is not just about Gaussian mixture models. In fact, if in Gaussian mixture models, so we can write down a probability model by saying it was P of x given z of Gaussian, right? So if you tell me what z was, the probability of x was a multivariate normal, and the probability of z was categorical. It was some discrete distribution over z. And together, that combination I was calling a Gaussian mixture models. But I could make different choices for each of these two. I could choose x to be multinomial or categorical or something, right? And z, same categorical, and it would be a mixture of multinomials. Just like this was a mixture of Gaussians, this was a mixture of multinomials. Right? In fact, there is a particular model called latent Dirichlet allocation, which is essentially x being categorical. So now x is a discrete variable. X can take values from 1 through k. And z becomes a Dirichlet distribution. You've seen Dirichlet before. A Dirichlet distribution is a density function on the simplex. Right? So z is a vector which is k-dimensional, which sums to 1 and is positive. So you first sample z, then you sample x. Does that make sense? Z is Dirichlet, and x given z is categorical. Does that make sense? And so that's a latent, it's called latent Dirichlet allocation from the paper that introduced it. Doesn't have that same sort of flavor of names, but we sort of understand that these are all instances of the same kinds of two-step models. First you sample some z, then you sample an x given z. Does that make sense? Okay. So in fact, so here's an example. This is a mixture of Bernoullis. So this is a digits data set. You are not told, so each picture is your x. So think of every single pixel here, just string it out into a long vector. Each pixel can be on or off. So each one is a Bernoulli random variable. You have a collection of Bernoulli random variables. And all I just give you are such samples of Bernoulli random variables, right? I don't actually tell you any labels. You can view these as running k-means on that data set, but it's not k-means, right? This is fitting a mixture of Bernoulli distribution. So these are the mean parameters and those are the priors. So you can view this also in terms of k-means as what are the cluster centers and what is the size of that, the relative size of that cluster. Does that make sense? So without knowing the identity of the digits, you're sort of discovering different clusters in the digit space. So this sort of looks like a 1, this looks like a 9, maybe that's also a 9, this could be a 4 as well, 0 and 3 or 8, 6, 0, 7 or 1, 5 and maybe 8. I'm giving it those names. You do not have any class labels or semantics associated with these, right? We're just sort of looking at them. Yes?
So like, the fact that there's 5 of them, 10 of them, that was just that big.
Yeah, that was handpicked.
Okay.
It's because we're domain experts, we know that there are 10 digits, so we'd like to see, well, what does it discover if I ask it to be 10?
Why isn't it like the digits 1 to 10, like why is it show 9, why is it?
Yeah, why isn't it perfect? It's because some digits are actually, like if you think about, there was a 4 and there's a 9, in pixel space they're actually quite close, right? It's hard to, you and I, when we look at digits, we look at certain attributes of those things, right? But we are feeding this as a long binary vector, and if you start computing Hamming distances, they're not too far. Does that make sense?
You had enough data where you eventually converged to...
Not necessarily. I mean, you're asking this sort of a question. I give you a bunch of points, and you're asking if you have enough x, would you really discover the clusters that I want you to discover? And that's a question not just of the amount of data, but also what objective function are you using? And if you keep using k-means like objective functions, which is reconstruction distances, like what is the distance from a data point to its cluster center, you may not discover it as long as you don't feed in a meaningful distance. If the distance is just Hamming like distances or Euclidean, you may not discover it, even with infinite data. Does that make sense? Okay. So what we're going to do is we're going to take this intuition a little bit further, and we're going to say, okay, this is still a particular kind of, each row is a particular latent variable or hidden variable model, right? In all of these models, z is unknown in the data, x is known. We're going to generalize this one step further and give you an EM algorithm for the completely general setting, and it will turn out that that general setting is basically it. Like once we can study it in that general setting, we'll write an algorithm for that general setting and it will tell us what we were doing for the Gaussian function. Does that make sense? So the general setting is going to be this, right? The general setting is there is some x which is observed, there is some z which is missing. You don't observe it in training data. There is some probability, like you'd like to estimate parameters. You'd like to estimate the parameters which maximize the log likelihood, right? I'm not telling you what P is. It doesn't really matter for this derivation what P is. Because all that matters is you need to be able to handle this. You just need to be able to maximize sum over data set, log sum over the missing value. So you have to marginalize out Z and you need to be able to do this. Does that make sense? Gaussian mixture model fits into this because you write this down as probability of x given Z times probability of Z. The Z is categorical, x given Z is Gaussian. But they could be some other terms. We're going to study this in the fully general setting, except maybe the fact that we'll keep Z discrete. The math is easy, right? I don't like integrals. But other than that, in that general setting, once we study that, it'll pop out an algorithm that will tell us what we were doing for Gaussian mixture model. Does that make sense? And because we didn't make any assumptions, that same algorithm will apply when you plug in different x given z's and different z's. Does that make sense? Okay. So this is what we'd like to do an argmax over theta. The problem here is there is a summation sitting inside the log, and that's coupling all of these terms together, right? And we'd like to get this summation out of the log. And we're going to do that with a particular trick that I'll introduce to you today. Maybe some of you are already familiar with this, but it's a really nice mathematical, yes?
Log sum trick?
Not the log sum trick. The log sum trick actually comes up when you actually want to compute the log sum x trick It's when you want to compute that thing and you have numerical instabilities. This is slightly different. Anytime you sort of face this sort of a thing, where there's a summation sitting inside the log and you have a probability and you'd like to move that out, a common sort of mathematical trick that comes up is something called Jensen's inequality. Anybody heard of Jensen's inequality? What is Jensen's inequality?
F(x) is convex.
Yeah, go ahead. If fx is convex,
F(x1), F half x1 plus x2 is less than or equal to half Fx1 plus half Fx2.
in a way, yes. So a more general way of saying that. Yes, so here's the goal, right? So theta hat is equal to R max over theta summation I equals 1 to n log summation over z probability of x equals xi z equals z comma theta. This is what we'd like to handle. We don't like the z sitting inside. It would be nice if it was outside. Here's the Jensen inequality sort of little tutorial of Jensen inequality. This is a concave function, right? It's some sort of a concave function. Here's what you know about concavity. Like this, the f of z, this is z1, there are 2 points, this is z2. The definition of concavity says that lambda times sort of f of lambda 1 z1 plus lambda 2 z2 is greater than equal to lambda 1 f of z1 plus lambda 2 f of z2. Right? That's the definition of concavity. That when you take 2 points, so not just for any lambda 1, lambda 2, this is for lambda 1 comma lambda 2, both positive, lambda 1 plus lambda 2 is equal to 1. So if you take a convex combination, so if you take 2 points, the convex combination of those 2 points, the function value of that lies above the convex combination of the 2 function values, which has this geometric interpretation that the line joining 2 points always lies below the function that you're doing. That's, in some sense, that is the definition of concavity. You may see it as the definition of convexity by inverting signs. Okay, so the key thing here is I can write this as summation lambda I zi I equals 1 through 2 greater than summation lambda I f of zi I equals 1 through 2. Right? That's the definition of concavity. That's just a way to write it. Jensen's is just 2 replaced by k. That's Jensen's. Right? That's it. It's just saying that if instead of 2 points, you had chosen some k points, a convex combination, a convex hull of those points, the function value of that would still lie above the convex combination of the function. Right? Just had to be born earlier to have a bunch of generalizations named after yourself. That's Jensen's. The reason why that's important is, if you think about it, here now it's not 2, right? So it's the fact that lambda I is positive and summation of lambda I sums to 1. I from 1 to 3. It's some number. Anytime we see this, we know what this is. This is a simplex. Right? Lambda lies on the simplex, which means lambda is basically a probability mass function. Right? There's some k-dimensional probability, and it's just telling you the probability of picking something. Right? So I can view this as an expected value. Right? This is the probability of something. This is the value z. So this is the expected value of z. So the probabilistic view. So the probabilistic view is, this is f of expected value of z greater than or equal to expected value of f of z. Right? Does that make sense? Excellent. And this is beginning to look a lot like this thing that we have. Right? Log is a concave function. That's kind of why I drew this function like that. log is a concave function. There's a summation sitting inside. That's this summation, right? And if we can express this quantity, as an expected value of something, then we will have a lower bound on it, which has the summation sitting outside. Basically, the summation goes outside the function. Right? That's what. Does that make sense? So far, so good? Okay. So the good thing is, log is concave. We have something that almost looks like a summation of a probability times something, but not quite, right? We don't really have a function. So expected value. The other thing that you could do is you can also say expected value not just of z, but some function of z. Right? So you can do this. F of expected value of g of z is greater than expected value of f of g of z. Right? Just doesn't matter. Define g of z as a new variable, right? That's basically. So we're getting there, almost there. We need that to show up. We need an expected value to show up. And if you really, really want an expected value to show up, you can make it show up, right? Here, multiply and divide by a distribution. Q of z divided by Q of z. Some distribution, I made it up. It's a distribution over z. Z are some discrete states, right? We haven't even defined what z type of variable is. It's some discrete variable, I made this distribution up, one for each data point. And now I have what I want. This is a probability. These two together are some function. This is an expected value. And that's a concave function. Does that make sense?
We could have directly written px and z as px given z to pz. That will be the same.
We could have tried that. The reason why I'm doing this is to illustrate the fact that you could introduce any kind of distribution. It doesn't have to be that particular distribution. And it will become a variable in our system. And we will optimize over that variable. And it will have a connection to what you're saying. So we don't have to sort of magically know what the answer is. It's just the optimization will tell us that that's the answer. Okay, so this thing right here is basically expected value under Qi of z of probability of xi over z given theta divided by Qi. That's what this thing is. Does that make sense? This one is participating, so this is probability times a function, summation over all states. So it means it's an expected value under this distribution of this thing. Does that make sense? So far, so good? Okay. And that's what we needed. This is exactly what Jensen asked us to do, right? Because now we have log of expected value, and that's what we know we can lower bound. So suddenly we get this nice little lower bound which says sum over all data point, and now it's a summation over all z, Qi of z log probability of xi comma z given theta divided by Qi of z. Does that make sense? I just applied Jensen, so f of expected value is greater than expected value of f of z. So here's the expected value, and this is log or f of whatever that function is. Does that make sense?
How many summations here?
There are two summations. One is over the data points that always existed. There was another summation over the z or the states of the hidden variable, and that got swapped with the log, and that's why that's sitting out. Yes?
While replacing, how are you making sure that the maximum of f of expectation is same as the maximum of this one? Like the parameters which you are going to end up is same.
Yeah, excellent question. So I want to take an argmax of that. Is that the same thing as an argmax of a lower bound? No, in general it is not. But that's fine. What's going to end up happening is this is a difficult function to optimize. And I'm going to say that I'm instead going to optimize a lower bound of that function. So if I can achieve a high lower bound, I know the true value can only be higher than that. Right? So I'm going to take an argmax of this lower bound, and I'm going to say if I can achieve a max value of say 10,000, I know the true value is only larger than that. So any function, any parameter that achieves even a lower bound or a function value of less than 10,000, I know it's no longer the argmax. Does that make sense? But in general, we talk about the sort of what can you say about the optimum of this compared to the optimum of this. Okay. So the important thing to, like, just sort of stepping back, this was our objective function. It was marginalized log likelihood, right? So marginalized log probability of this parameter. We wrote down a lower bound on that, and that lower bound is something that now depends on two things. It depends on our original parameter, and it depends on all these distributions that we introduced. So this is our lower bound, and this is greater than equal to the lower bound. Does that make sense? So this is our lower bound, and now it's a function of the parameter, obviously, but also these arbitrary probabilities that I multiplied and divided by. Does that make sense? I could have chosen any distribution over a discrete variable. Right? And basically now what we're going to do is we're going to ask for the tightest lower bound. This is something that we want to maximize. I'm going to ask for the tightest lower bound by maximizing both over theta and q. Right? Theta is some parameter. Think of a Gaussian mixture model. Theta are the mean parameters, the prior parameters, the covariance matrices. Q's in a Gaussian mixture model, we haven't yet defined what was this in a Gaussian mixture model. It will turn out that in a Gaussian mixture model, the reason we compute probability of z given x is because this Q, once you optimize over it, the optimization will tell you that you should compute probability of z given x. Even we multiply by some arbitrary distribution. Does that make sense? Okay. So I'm going to erase this part so I can expand on this idea. Yeah.
So in this, we know that what values of lambda give us equality.
Do you know what values of lambda give us equality? Lambda here are q's here, right? So what values of q make the lower bound tight? And we are going to search over lambdas or q's. So we're going to ask for the tightest lower bound. Whether the tightest, so this left-hand side is greater than right-hand side, we're going to maximize the right-hand side. If we hit equality, then that's great, right? So the tightness is exact, there's no loss in approximation, and it'll turn out that we can actually do that. We can search for the lambdas, we can search for the q's, that gives you a tight lower bound. That makes sense. So here's what I'll do. This is a lower bound. I'm going to write down a coordinate ascent algorithm. I'm going to fix thetas, maximize over q's, fix q's, maximize over thetas, and I'm going to alternate over those. And I'm going to show you what each of those steps looks like. It will have fairly intuitive interpretations once I'm done. It will look extremely messy while I'm continuing, but hang in there. It's like there's just going to be two steps, coordinate ascent on one and coordinate ascent on the other, and it's after that it's all pretty pictures, right? So that's the math extent of it. Yes?
In this case, we have log function, which is a monotonous function.
Yeah.
So won't this hold that maximizing an upper bound, so argmax, even the argmax of the lower bound should be same as the argmax of the true function because it is a monotonous function?
I think you're mixing two different arguments. We have made the argument in the past that argmax of, if you're trying to do argmax of g of x, then argmax of log of g of x is the same thing because log is a monotonic thing. But that's not the argument being used here.
No, I was not comparing with that. So if you have, let's say, just two log functions, you don't have any summation.
Okay.
So if this is like a higher log function, so if I take argmax of that comes somewhere here. If I take a lower log function, so the argmax would be same, right? Because if I shift somewhere here, So that will change because both are log functions. But here summation is also involved, so I'm not sure whether that will hold or not.
Yeah, in this case, it definitely doesn't hold in general. It is not the case that every time you have a summation of logs. So first of all, that argument only holds for a single log, right? Log of G1 plus log of G2 is not the same as log of G1 plus G2, right? For example, that's log of G1 times G2, and so you're not taking the odd maximum. Okay, so stepping back, we have a function on these two things. What I'll do is I'll write down coordinate descent steps, and it'll have sort of intuitive interpretation. So here, let's do the first one first. I'm going to say, so the first thing here is sort of, in this algorithm, initialize theta 0, right? Just come up with some parameters, just come up with a guess. In a Gaussian mixture model case, it would be the Gaussian cluster centers, the covariance matrices, the prior parameters. Okay. The second thing you do is you fix theta t at any given time t, right? You fix theta t and you maximize over all. Okay, so this is going to be a little problematic. I have thetas and I have q's. They look similar, but look for the diagonal one. Okay, so theta t's are fixed, and q of z's are the distributions for all i's. I going from 1 to n. All of these, we're trying to maximize this lower bound over all of those. Does that make sense? Okay. The first thing I'm going to do is I'm going to actually, I can do that here. It's not that hard. Here's something that I can do. I can write this down as, and this is a trick that Chetan was suggesting. This is a joint probability, and I can write down, I can do chain rule for this, right? So I can write this down as probability of z given xi, theta times probability of xi given theta. Right? This is not an approximation. I've just written down chain rule. This is still the joint distribution. And I've done this particular thing, z given xi, because I know what's coming. Right? I'm trying to make a particular relation, not xi given z, for example. Okay. What I'm going to do is I'm going to write these two terms in the log as one expression, and this term as another expression. Right? So here's what that summation becomes: summation over I, summation over z. So qi log term 1, term 2. So qi of z log probability of zi, z given xi, comma theta t at time t, right? Given qi of z. This is one term, and the second term is summation over I, summation over z, qi of z, log, I have p of xi given theta. Does that make sense? There's a log a times b. I just split that up into log a plus log b, and so all the multiplicative factors are going to do. Okay. The reason why I did it is because if you stare at this, this one depends on x. It doesn't depend on z. There's no z term here. So the summation over z is over some distribution times some constant. Right? So I can take the constant out of that summation, and basically this distribution will sum to 1. And so there's a summation over I, the summation over z is gone, there's just log probability. I'll finish in a few minutes and we'll stop after that. So there's a log probability, right? That's log likelihood. This is exactly what we started out optimizing. We're back at the same thing, right? Before we did all the lower bound stuff, this is what we started out optimizing. But this is a constant with respect to the optimization variable, which is q. It does not now, after q summing out, this does not contain any q. Okay. This term, some probability log some other probability divided by some other probability, does that look like a term that you recognize? KL, excellent. This is actually negative KL of Q I of z with respect to probability of z given xi, comma theta at time t. Excellent. So if this is a constant, you'd like to maximize this term, which means you'd like to minimize this term. So you'd like to minimize the KL divergence between this arbitrarily chosen distribution and this particular distribution. What is the arg min of that? Same is exactly. If you have two distributions, you want to get the argmin, just set them equal to 0. You will get an argmin of 0, right? You've proven this in homework 0, right? You know how to do this. You've been waiting for this moment the entire semester. There's somewhere going to be an argmin, so you can have that answer. Yes, this is that moment. So the argmin of qi star, if you will, or qi p, if you will, is just set it equal to p of z given xi, comma, theta t. Right? If you think about this, this is what we did in Gaussian mixture models. We said initialize the Gaussians with cluster centers, covariance matrices and everything, and then compute this distribution, which is the probability of assigning, assigning this data point to this cluster center. Does that make sense? It was not an arbitrary choice. It was illustrated by the lower bound given by Jensen's and performing coordinate descent. It was the tightest bound that we could get. In fact, not only is this the tightest bound, this is a tight bound. This is a tight lower bound. If you think about it, this is KL. You do the argmin, what is the KL equal to? 0. So this is the only term that's left. That term is, the Q's are gone, right? So this is gone. So the only thing left is summation over I of log probability. That's what we started out with, right? Summation over I of log probability of x, because z was summed out. Right? So we gave a lower bound. We optimized that lower bound with respect to Q, and we were able to get a tight lower bound. Right? Does that make sense? So it means this is a lower bound maximization problem where every odd iteration, your lower bound becomes tight. Because every time you maximize, so there's going to be a fixed theta maximize Q, fixed Q maximize theta. Every time you fix theta and maximize Q, your lower bound suddenly becomes tight. Does that make sense? Everybody with me so far, hang in there?
Why did you erase the Q?
Why? Because this one doesn't depend on z, there was a summation on z, so the distribution sums to 1. Okay, so this is called the E step, or the expectation step, because it asks you to compute the expectation of an indicator variable, which is the probability of this conditional distribution. Does that make sense? You're computing an expectation with respect to this Q, which is what leads to this. That's what Gaussian. This is why we were doing this in Gaussian mixture models, because it was coordinate descent on the lower bound. Does that make sense? Okay. So just one, hang in there with me, just the other direction. I'll write the other direction and then we can take a break. Okay, so the other direction is you fix Qi of z at time t, right? And then you maximize over theta. Right? So we're searching for the best parameters given this assignment of Q. So theta of t plus 1 is equal to argmax over theta of summation of I, summation of z. And now this is what we need, right? And now what I'm going to do is I'm going to multiply this again because I need this to be joint distribution. In this direction, I don't need this sort of a thing. So I'm going to write down Qi at time t of z log probability of xi comma z theta. Okay, that's the argmax that we have to do. But now, if you stare at this we already know the Q, and so this is just an argmax. Wait a second. I'm missing it. Thank you. Okay. So I need one more trick. Okay. I z qi at t at z log probability of xi comma z comma theta plus summation of I summation of z I and z log perfect. So that's what I copied over from this side. Right? This was Qi log joint distribution divided by Qi. That's what this says. And what I just was, this was log A by log B. I mean log A by B, and I wrote that as log A minus log. And the good thing is this part is constant in this iteration, right? Because I already know what these Q's are. This is a constant, right? This is just the entropy of all those Q distributions, but we don't really care because they don't contain theta. This is the part that we want to optimize. And this is the only part that we want to optimize. And now this is much easier because this looks like a fully labeled data set. You already know what we already know what these Q distributions are, so ignore them for a minute. Just forget about them. There are some numbers, right? It's this log probability, and this is really nice. This means that if someone had given you a data set with this xi and this zi already labeled, you just have to maximize the log probability, right? In some sense, this means that your data set essentially consists, it looks like this. Your data set has x1 labeled as z equals 1, all the way till xn labeled as z equals 1, and x1 labeled as z equals 2, and x1 labeled as z equals 2. Right? So x1 is labeled every single thing. Right? So imagine this data point is labeled with class 1, labeled with class 2, labeled with class 3, all the way to labeled with class k. And that's just not for the first point, that's for every single point. So you see xn labeled with z equals k. Right? This is your data set. It's n times k, that many data points, except it's a soft data set. Every single data point has also a weight. So this is qn of 1, qn of k. Every single data point comes with a weight. And that's what the log likelihood looks like for that fully observed data set. This is what was happening in Gaussian mixture model's case. Every single data point was labeled with every single Gaussian cluster center. It's just with different soft posterior distributions. That's what I was showing as a pie chart in that thing. Which means now all you need to do is, there's some black box function that you already know how to maximize this. And for a Gaussian mixture model, that black box function was compute weighted means and weighted average, weighted covariance matrices. Does that make sense? So that's the two-stage procedure. The one stage is, fix the parameters of your model, optimize these Q distributions. It's going to lead to a tight lower bound, which is going to ask you to compute the conditional probabilities. The other step is fix these conditional probabilities and find your variables. And this time, you'll basically assume that your data set has every single x labeled as every single z. Does that make sense? And notice we did not assume anything about probability of x given z or probability of z, right? These could be arbitrary mixture models. And that's why you can apply this to Gaussian mixture models, multinomials, whatever. Okay, so let me show this one picture. Hopefully, wake people up. Alright, so this is what this visually looks like. On the x-axis are some one-dimensional parameter space. This is just some one parameter because I'd like to view this as a plot. The red curve is the marginalized likelihood. So it's the log summation of z, and it's some non-concave function. Every time you pick a particular parameter theta, you're coming up with a particular Q distribution, which leads to an approximation of this non-convex or non-concave function by this blue curve. You can find the argmax of this blue curve by taking a closed form step, right? That closed form step is just find the posterior distribution, P of z given x. And so you update x, and at this update theta, and at this theta, you find another lower bound. Notice that each point after you take the step, the bound is tight. So at this point, the lower bound, which is the green curve, is tight at this point, and the lower bound is also tight at this point. Does that make sense? So this is an illustration of coordinate descent that's going on in the Gaussian mixture model case and in the general case. Okay, let's take a minute.
It already looks how it's going to converge. It overshots the real max. Then it goes back.
No, it won't do that because if you think about it, depends on the local shift at that time.
So it has to. So the green
also start with
Sleeping. Sleeping is party. It's the party is That's gonna sound not what I was So I just like went to like like a block. So I will probably and then I'm like, very true. Really?
我如果把它带入高层，它也不是这样，它是需要建高层这样的。因为这样算是真的所以说是上一个说的他们会说这两个谁来分析
but it's not a maximum of
All right, settle down. Let's pick up from here. The thing to remember here is, sorry, can you settle down? The thing to remember in this whole thing is not the sort of inner workings of these derivations. You'll find them in the notes as well. The sort of step back and sort of the message to take away from this is we have this happens a lot, like when do latent variables show up? Latent variables show up in clustering problems, in density estimation problems. Sometimes latent variables or hidden variables show up when you have missing data. Here there was a nice separation between X, which was always observed, and Z, which was always missing. But a lot of times you can also have the case where you measure some data set and certain features are missing. Right? Certain features are missing because either that sensor broke down or it's sort of a human response and you forgot to ask certain questions to the human or they did not answer. And so you have sort of rows of your features where some entries are just sort of missing. You don't have that value. Right? Even though the math I did here was sort of cleanly separated, there was an X which was always observed, Z which was always missing. The same sort of argument applies even to the cases where per data point basis there are different observed and different missing features. So on data point 1, maybe the first feature is observed, the second is missing. On data point 2, maybe both are observed and actually the third one is missing. Right? But the notation becomes slightly heavier because now you have to keep track of Z sub I as opposed to just a Z, but the same argument goes through. The way the math looks like, what it asks you to do is something extremely interpretable. What the math is asking you to do is construct, from the features that you have actually observed and the current setting of parameters, which are your guess, construct your best guess or your distribution, what do you believe about the missing features? Right? What do you believe about the missing variables? That's your Q distribution. Now just pretend that that's reality. Whatever you estimated, just pretend that that's reality and take an average likelihood under all possible cases. And just pretend that actually the missing feature was 1, it was 2, it was 3, with some probabilities. And just use this soft data set to learn the parameters later, and just repeat. Right? It's an extremely sort of intuitive interpretation, which actually, people have been doing this before this idea of Jensen's and lower bounds and like this sort of formal connections with it. This is just missing data imputation, right? A lot of times when you have a data matrix that you measure and there are some missing values, what do? Well, one thing I could do is I could look at the average value of this missing feature from the rest of the data points or something, right? And that's similar to the ideas here, right? You're basically computing a distribution of what do you believe from everything else that you have observed, whether that's from this point or some other points. Does that make sense? Yes.
So what's the theta here?
The theta are the parameters of the model, right? So in the Gaussian mixture model, thetas are cluster centers, cluster covariances, and
so it can be any form here.
Yeah, so this, that's kind of why we did the general setting. This theta can be, I didn't tell you what probability of x given z was, I didn't say what probability of z was, I didn't say what theta was. And then it's because we wanted this derivation to apply for anything.
So last time we did the EM for learning GMM
Yes.
parameters. So
Yes.
that's like a special case.
That's a special case, exactly. EM for learning, Gaussian mixture model is a particular kind of latent variable model. It has x variables, which are your data points. X given z is Gaussian, probability of z is categorical. And the same EM applies, and that algorithm that we introduced came out as a special case, which by the way contains k-means as a special case. Because k-means is hard EM with under certain assumptions. Does that make sense? So we've been sort of going generalized, all the way to this just abstract algebra. Okay. All right, so so at this point, we are essentially done with clustering, k-means, Gaussian mixture models. Here are things that we want you to know and understand. We want you to understand what k-means is doing, obviously the algorithm. For example, you can imagine us asking you questions like, what happens if I change the distance function that k-means uses, right? In fact, is that one of the questions in the homework?
Yes.
Oh.
L1.
I was trying to figure out whether that's in the homework or the exam. It's a good thing that it's in
You landed on the wrong line.
What? Yeah.
You landed on the wrong line.
Or the right line, depends whose opinion you're considering. From your perspective, yes. So, for example, if you change the distance function that k-means uses, what sort of probability distributions can we connect that to, and what does that relate to as argmax of some log probability or something, right? You should understand EM not only for just mixture of Gaussians, which is an extremely simple algorithm, but also for the general case, and you remember that it is coordinate ascent, there are no guarantees, it may get stuck at local maxima, so the pictures are fairly sort of illustrative in these cases, that there is some non-convex objective function, you're sort of computing a non-concave objective function, you're computing a concave lower bound, and so you can get stuck. Does that make sense? Okay, so let's move on. So at this point, we've gone through a bunch of these tasks, and like the last task remaining for us is this idea of dimensionality reduction. And it's this idea it's an extremely simple illustrative idea of PCA, or principal component analysis. And you'll hear just to tell you, you'll hear these terms, you'll hear terms like principal component analysis or Carhoonen-Louvre transform, or the signal processing people are familiar with this. KL transform is something that signal processing people study. If somebody's taken like stochastic signals in class, you've sort of already met KL transform, but we won't assume that you know it. You'll hear terms like eigenfaces, which was an algorithm applied to do dimensionality reduction and classification in sort of face recognition. So it was this algorithm right here, this picture, to take a data set of aligned faces and to come up with these things that are called basis vectors or eigenfaces and sort of express these as a linear combination of those. That was sort of the first computer vision application of the idea of PCA. And since then, it's sort of become like eigen whatever, like eigen fingerprints, eigen insert your problem domain, and you can get sort of that out. PCA is one dimensionality reduction algorithm. There are many other dimensionality reduction algorithms that you hear. The idea of dimensionality reduction, which is what we'll try to get to, is that a lot of times you have data that is living in an extremely high dimensional space. So for example, if you think of an image as a matrix, each pixel is an entry that's telling you density, or you may think of it R, G, and B planes, so it's giving you 3 values for every pixel. If you sort of string that up into a really long vector, it can easily have 5 million dimensional vector, right? But we somehow don't believe that your data actually lives in a 5 million dimensional space, uniformly occupying space, right? The kinds of images that you end up capturing are not IID over this 5 million dimensional space. Does that make sense? So what we'd like to do is we'd like to go from a high dimensional space to a low dimensional space and represent data with fewer dimensions. The reasons may be easier learning. So for example, we know that ultimately we're going to do some classification problems with this, so lower dimensions would mean that lower parameters for a linear classifier, for example. It could be visualization. So a lot of times you can't visualize anything more than 3 or so dimensions, right? 4, yeah, you'll have to do some notion of time and sort of arrange them in some way. But 2 is nice, 3 is already clunky because MATLAB, for example, gives you lots of problems. You'll have to build sort of 3D visualizers. 10,000 dimensional spaces, we have no idea what's going on. In fact, when we were looking at nearest neighbor distances and things like that, we argued that humans in particular, we have no intuitions about 10,000 dimensional spaces. Right? Algebra tells us something is true that seems extremely unintuitive to us. That if you just sample a point, 2 IID random vectors in a 10,000 dimensional space are with extremely high probability, always orthogonal. Just sample 2 vectors, compute the dot products, you get a 0. Right? And that's because central limit theorem is key. Right? So we'd like to sort of bring things down to a lower dimensional space, and in some sense we'd like to discover, which is quote unquote called the intrinsic dimensionality of data. We believe that our data does not occupy a high dimensional space, it lives in some lower dimensional subspace or manifold. A subspace, so if you think of a subspace is sort of like a hyperplane passing through the origin. So for example, if you in your data set, you go ahead and you measure 2 quantities, right? There's one x1 and the second thing x2. I'm not giving them names in particular, but let's say you sort of observe your data, and this is not class labels, this is not a regression problem, these are just your inputs, right? Let's say this is what you sort of observe as plotting your data. Even though this is a 2-dimensional data set, it is clear that you have sort of roughly measured some 1-dimensional concept with some noise, right? It's clear that your features are essentially correlated or measuring the same thing. Right? If they are identical with very little noise, then you have some bug in your code, right? You may have measured the same thing, or it may be slightly scaled. You may have measured something in 1 unit, and you have that same thing measured in other units. Right? So we'd like to discover, so this is a low-dimensional subspace that your data lies on. It is not a 2-dimensional data set, it is a 1-dimensional data set. We'd like to discover this. Right? Or it could be that it's not a sort of linear subspace, it's some sort of manifold, and I'm sort of drawing an arbitrary curve shape out, but it could be that all data roughly comes from this, with some noise. Right? Maybe I plot my data set out and it looks like it's lying on some surface. The problem in a lot of these things is the dimensionality of the raw things that you measure may be extremely high, so I can't really plot this, right? I don't know how to, what way to visualize this. Okay? So we'd like some way of discovering what are the dimensions that matter in our data set. And if you compare this to clustering with k-means, we again run into this problem. What is the objective function? Why are we doing this, and how do we measure progress, right, or performance? And we run into this same issue that you have to define your own objective functions, right? Because there is no task loss. Like how do I measure what is a good visualization? Right? I have to involve a user in the loop. Maybe they were trying to find something. If it's a user discovery time, it's not something that I can optimize. Right? So we're going to have to write down objective functions and say that these are reasonable objective functions, and that's why you can write multiple ones, and that's why there are multiple algorithms. Does that make sense? Okay. So here's sort of the first illustration. Of course not. Here's the first illustration of the concept. We like Okay, so what we'd like is something like this. We'd like a system that when I give it some data that looks like this, I want the system, when I click a button to say, here is this one-dimensional subspace, right? Notice that it's a two-dimensional data set. This is the center, the mean of my data, right? I can always find this mean by just taking the average of my data points. But here is an axis. This is that one-dimensional axis that tells me most of your data seems to be like this one-dimensional data. It's lying on this subspace. Right? Another way of thinking about it, and we will formalize this, another way of thinking about this, most of your data seems to have variation along this axis. And there's very little variation orthogonal to axis. That's the maximum variance view of PCA. There is another variation which is going to be there's another view of PCA which is going to be if I take my two-dimensional data and I project it down to one dimension, this is the direction I should project onto. I should not project onto this direction, in which case all of the data points will come here and they will have very little distance between them, but I should project them onto here, because when I try to reconstruct from this, I will have high error. So there's the min reconstruction error view of PCA, there's the max variance view of PCA, and KL transform is the orthogonalization view of PCA, which is I have two-dimensional data, so my x1 and x2, my features are correlated. I'd like to transform the coordinates of the axis so that my features become uncorrelated. So if I think of this as one coordinate, my new feature, and I think of this as the other coordinate, so no dimensionality reduction yet. It's just a rotation and shifting of the feature space. This two-dimensional feature space is now nicely uncorrelated. My data is somehow orthogonalized to this. Does that make sense? It turns out all three views, min reconstruction, max variance, orthogonalization, lead to the same interpretation. You should do PCA or something which is known as, you end up basically doing eigen decomposition of the covariance matrix. Does that make sense? Okay. Here's another sort of really nice illustration of this concept that I really like. This is really nice user interface. So think of this as these are the 5, 1, 2, 3, 4, 5. These are the 5 points that you have measured. Right? This is the same example that we've been using. You went ahead and measured 2 dimensions, and it seems like most of your data seems to lie on this one-dimensional space. This is the output of PCA, those 2 axes, and we'll tell you what they mean. They are centered at the mean of the data set. The origin of your new coordinate space, new 2-dimensional coordinate space, is the mean of your data set. And what you're doing from here to here is you're basically making your axes now the correct axes, right? The dimension PCA dimension 1, PCA dimension 2 are the new axes of this plot, and therefore most of these points have variation only along the new x-axis, the new dimension 1, which is this red dimension. Does that make sense? And they do not have too much variation along the green axis, which is this green axis, and so they're mostly lying on this one-dimensional plot. Does that make sense? Right. And here are the x and y values for each of the data points, and here are the x and y values in this new 2-dimensional space for these data points. What you notice is that most of the, so first thing you notice is they're kind of centered around 0. I'll scroll this up. So the first thing you will notice is that this data is not centered in the sense that its mean lies around 4.5 and 4.5, right? That's what these things are indicating. So the means of the data set are around 4. this is a centered data set, right? So this is the new origin, and so most of your data is roughly around, most of your data is centered. It's centered at 0. The mean of the new data set is 0, 0. But more importantly, most of the variation in the data points seem to be on the red axis, the first axis. The green axis has very little variation, right? And what we can do is we can sort of take a data point, move it around, and we can see what PCA would do. So as long as we stick to this one-dimensional subspace, nothing changes, right? The only thing that changes is the mean of the data set. Right? That's all that we're affecting. The y coordinate stays exactly the same, and the green direction stays exactly the same. The thing that changes though is, so pay particular attention to, how do we do this? So pay attention to these points. When I move that data point, only one point changes here, right? All the rest of the points are staying the same. Why? Because the coordinates are exactly the same. So the rest of the 4 points change. But as I move that one point, all points change here because it is changing the origin of the thing, right? Does that make sense? All right. And I can obviously try to sort of break this assumption of low dimensional thing. I can sort of take this one far, I can take this one far, and then it's still fine. It still finds that same one direction and same in the other direction. I can sort of try to make it point in arbitrary sort of ways, right? So we're trying to fit a one-dimensional thing to it. And this is what the transformed feature space looks like. Does that make sense? Alright, so this is that same idea except in 3D, right? This is a three-dimensional data set. So this is the original axes, right? So there's a red axis. This is the original three-dimensional axes. That's each dot is a data point, and what I can do is I can ask for here. So I can ask for different PCA directions, right? Those green, red, and blue are the PCA new coordinates, if you will. I can sort of move them around. I can ask for different coordinates, and what that changes, it doesn't change the original coordinates, obviously. It just changes my projections after I project it onto the new coordinate space. Right? Notice that there's no dimensionality reduction here yet, but if I do PCA, what it'll do is it'll find these three directions such that the first dimension after PCA or in the PCA direction has highest variance, the second dimension has lower variance, and the third dimension has even lower variance. Does that make sense? And the idea of dimensionality reduction will come in the sense that at some point there will be so little variance in that direction that you just throw it away, right? Which is what was happening in the 2D case as well. If most of your data is living on a line, find that line, and orthogonal to that you can throw away. And orthogonal to that could be an entire subspace. Right? If you're living in a 10,000 dimensional space, you find this one line or direction, everything else is orthogonal to that, throw it away. Suddenly you've done dimensionality reduction. Does that make sense? Okay. Here's another really nice example which sort of shows why this is a non-trivial thing. Right? Everything so far was 2 and 3D. You and I could visualize it. Here's the sort of data set that we deal with in practice. Right? You can't visualize this. It's actually measuring consumption of alcoholic drinks, beverages, blah, 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 different types of food items for people in 4 different countries. The dataset creators know that there's actually 4 different countries, but pretend that this was all coming from a single country. Right? You sort of aggregated everything. Once you do this, turns out here's the first dimension. Right? In that first dimension, these 3 are pretty close, and that one Northern Ireland is extremely far apart. Why? It turns out that they are like, this coordinate doesn't have a name. We had a name for every one of these features. We don't have a name for this new coordinate. It's just some direction pointing in this space. Turns out that I think it's potatoes. Potato consumption is extremely high in Northern Ireland, and their consumption of fresh fruits is extremely low. And you combine a whole bunch of those things, and it turns out that they're a statistical outlier. They just eat differently. And that's something that you can discover when you see something in a low-dimensional space, like a 1 or 2-dimensional space, but you can't discover that by looking at a 17 or a 20-dimensional space. Does that make sense? Okay, so this is the idea of PCA, and let's stop here. What we'll do next time is I'll show you PCA, we'll look at the theory of PCA, and we'll show you how these images can be taken, and these are basically the directions or the bases vectors that you can extract from your data set and how they make sense. Right? We'll pick this up.